Hello friends, in today's lecture we will see some test to check whether the series is convergent or not. Okay, that is, we will see test for convergence of the series. There are various tests which have their different criteria to check whether the given series is convergent or not. Okay, so first we will see comparison test. Okay, so our topic is test of convergence. Okay, convergence test for series. So first type is comparison test. Okay, the first type is comparison test. So in this type comparison test there are three subtypes. Okay, there are three comparison tests. Okay, so first type is direct comparison. Direct comparison test. Okay, direct comparison test. This is the first type in this point, that is comparison test. So what is comparison? We always used to compare. Suppose this is this number is greater than this number. For comparison, that so this number is has bigger value than this number. Okay, such a comparison. So here also comparison test, we have to compare two series. Okay, first we will see the statement of the direct comparison test. Okay, so the statement of this test is, suppose there are two series, series xn and series yn, where xn is the n term of the series and yn is the n term of other series. Okay, so let xn and y, so let xn is greater than or equal to 0 and y also greater than or equal to 0. These are the two n term of two different series. Okay, and suppose there is natural number m and some constant say k. Okay, such that this xn is always less equal k times yn for all n greater than or equal to this m, where this k is some positive constant. Okay, so from this we observe that if there are two series xn and series yn, such that the n term of this series yn is always greater or equal to the n term of the series xn. That is, here after some terms, here each term is greater than each term here. That is, in simple way we can say this series is greater or equal to this series, or the terms of this series are greater or equal to terms of this series, excluding some finite number of terms. Okay, so if this is the case, then the direct comparison test says if the bigger series yn is convergent, then smaller series also convergent, and if the smaller series is divergent, then upper series or greater series also divergent. Okay, so we write down. So this implies then the series yn, that is the bigger series, the series yn convergent implies series xn is convergent. And this is the first statement. And the second statement is, what is the first statement? The first statement is, if bigger series is convergent, then smaller series also convergent. And second statement is, if the smaller series is divergent, then bigger series also divergent. Okay. And second, the smaller series xn is divergent, then the bigger series yn is also divergent. Okay. So this is the direct comparison test. Now we will see some example based on this test. Okay. So in the first example, we are given the series whose n term is 1 upon n square plus 2. Now we will try to find the n term of the series, which is to which we can check the convergence or divergence easily. Okay. For that purpose, we know the criteria for the P series, geometric series. Such series are convergent when they are divergent. We know, so we have to apply this to here to find the series yn. Okay. Now see here, 1 upon n square plus 2. But we know that the 1 upon n square plus 2 is always less than or equal to, actually strictly less than 1 upon n square. We can say it is strictly less than 1 by n square. So this is xn and this is our yn. So here the xn is always less than yn. But the series 1 upon n square, that is this series yn, whose n times 1 by n square, is always convergent. Why? Because it is a P series and the value of P is 2 is greater than 1. We know that the series 1 upon n raised to power P, that is P series, is convergent when P is greater than 1. Okay, we know the series 1 upon n square is convergent. Okay, since it is P series and value of P is greater than 1. Now the series xn whose n times 1 upon n square plus 2 is less than this series whose n times 1 by n square. So series xn is less than, or less, we can say less equal to also, is less than series yn, and the series yn is convergent. So by comparison test, the series xn, that was n times 1 upon n square plus 2, also convergent. So this applies series xn, which is equal to series 1 upon n square plus 2 is also convergent. Okay, by comparison test. Why? Because the series is greater than this series is convergent. We know if the bigger series is convergent, then series is less than bigger series also convergent. Okay, so this series whose n times 1 upon n square plus 2 is convergent by comparison test. Okay, now the series whose n term is 1 upon 5n minus 4. Okay, now we have 5n minus 4 is greater than 5n. Okay, because here 5n minus 4, sorry, 5n minus 4. Okay, 5n minus 4 is less than 5n because we are subtracting 4 from 5n. It is 5n, but here 4, we are subtracting 4 from 5n. This element or number is less than 5n. So if you take reciprocal, the inequality get changed. So this applies 1 upon 5n minus 4 is greater than 1 upon 5n, because here denominator is bigger, the denominator is smaller. This number is greater, this number is less. Now this is our xn, this is our xn, and this is our yn. So this series whose n term is this is greater than the series whose n term is this. But the series, now the 1 over 5 is constant. Now the series, okay, 1 by 5n. We can write here also one more thing. Again, 1 by 5n is greater than 1 by n only. So instead of taking 1 by 5n as a yn, we will take this as, so this is our xn and this is our yn. So we get this two series. The xn is 1 of n minus 4 is greater than 1 by n, which is yn. So here the series xn is greater than series yn, but the series yn is now the series yn is equal to series 1 by n, and this series is divergent. We know this series divergent either by using p series test. Here earlier p is 1, which is, we know p series is convergent if p is greater than 1, strictly greater than 1, then only p series is convergent. Here p is equal to 1. Also this is a harmonic series, and we also know by Cauchy idea this series is not convergent. Okay, but the series yn, which is equal to 1 by n, is divergent. And here the series xn is greater than series yn. Okay, so here smaller series is divergent. So by using comparison test, the bigger series also divergent. The series whose n time is 1 over 5 minus 4 also divergent by using comparison test. Okay, so by direct comparison test, DCT, direct comparison test, by direct comparison test, what can we conclude? The smaller series is divergent, so bigger series must be divergent. So by direct comparison test, the series xn is divergent. Okay, because the smaller series is divergent, the greater series is also divergent. Okay, then here we know that price n cube minus 1, this term is always greater or equal to the term n cube. So 1 upon twice n cube minus 1 must be less equal to the 1 upon n cube. But here we want n upon twice n cube minus 1, and here it is only 1 upon twice n cube minus 1. So for this adjustment, we multiply both sides by n. So this become n upon twice n cube minus 1 is less equal n upon n cube. But n upon n cube is nothing but 1 by n square, 1 n get cancelled, so 1 by n square. Okay. So now this is our xn, this is yn. So the series whose n term is 1 by n square, we know the series yn here, which is equal to series 1 by n square, is always convergent because it is p series. By p series test, so here earlier p is 2, which is greater than 1. The series 1 by n square is convergent by p series test. Okay, by p series test, and here this is the greater series. So greater series yn is convergent, and hence by direct comparison test, the smaller series whose n term is this also convergent. So by direct comparison test, DCT, here the greater equal series or bigger series is convergent, the smaller series also convergent. So by DCT, the series xn, which is given by the n term n upon twice n cube minus 1, is also convergent by direct comparison test, because direct comparison test says if the bigger series is convergent, the smaller series is also convergent. So this is the application of direct comparison test. Next type in comparison test is limit comparison test. So we have to find limit of something to conclude about the convergence of the series. Okay. So the statement is, let the series xn and yn be the two series of non-negative terms. That non-negative terms means the terms xn and yn are always greater or equal to 0 for all n. Okay, and limit n tends to infinity, limit of the n term of the series, this series, upon n term of this series. So limit n tends to infinity, xn upon yn is equal to some finite number L. Okay, some finite number which is not equal to 0 and infinity. It is finite means not equal to infinity, but though it is finite, not equal to 0, then series xn and yn converge or diverge, together. Okay, this is the limit comparison test. This implies if we take the limit of ratio of n term of these two series and it is some finite non-zero number, then both series converge or diverge together. That is, if the series xn is convergent, then series yn also convergent, and if series yn is convergent, then series xn also convergent. Okay, so both the series converge or diverge together. This is the limit comparison test. So we will see now example based on this limit comparison test. Okay, so let's example test the convergence of the series. Okay, test the convergence of the series. The series given as 1 upon 1 into 2 plus 1 upon 2 into 3 plus 1 upon 3 into 4 up to so. So we have to check whether this series is convergent or not. So by observation, we can say the nth of this series must be n into n plus 1. See, here 1 into 1 plus 1, that is 2. 2 into 2 plus 1, 2 into 2 into 3. 3 into 1, 3 plus 1, 4. Okay, so 3 into 4, 4 is 3 plus 1, 3 is 2 plus 1, 2 is 1 plus 1. So here the n term, the xn must be equal to 1 upon n into n plus 1. See, 3 into 4, 2 into 3, 1 into 2, n into n plus 1. Okay, this is the n term of this series. Now we take the series yn such that the n term yn is equal to 1 upon highest power of n. Now 1 upon n into n plus 1 is nothing but is equal to 1 upon n into n square into 1 n. The n of the series is 1 upon n square plus n. So we choose yn such that yn is equal to 1 upon n raised to power the highest power of n in denominator in xn. What the highest power of n in denominator is 2 minus highest power of n in numerator in xn. But here there is no n in numerator, so highest power of n in numerator is 0. So 2 minus 0 is 2. So we choose yn is equal to 1 by n square. This is one method to choose the series yn. Okay, you can choose the series yn by observation also, but this is the one of the method to choose the series yn. Now we will calculate the limit of the ratio xn upon yn. So limit n tends to infinity, xn upon yn is equal to limit n tends to infinity, xn is 1 upon n square plus n upon yn 1 upon n square. So upon 1 upon n square becomes in numerator just n square. So this is equal to limit n tend to infinity, divide numerator by n square. So here remains only 1. So here remains only 1. N upon n square is 1 by n. Now as n tends to infinity, 1 by n tends to 0. So 1 upon 1 plus 0 is equal to 1. And this is some finite number not equal to 0. So by limit comparison test, the series xn and yn converge or diverge together. Converge or diverge together. But the series yn is equal to series 1 by n square is convergent by P series test, and since both the series are convergent or diverge together and series yn is convergent, so x are also convergent. This is the limit comparison test. The two series, one of them is convergent, other must be convergent. If one is divergent, other must be divergent. But here, one series yn is convergent, which implies series xn whose n term is 1 upon n to n plus 1 is also convergent. Okay. So this is the limit comparison test. Okay.